Fine, let's start. Number 12. Rings that should not be. In 2020, a radio telescope in the Australian outback called ASCAP, the Australian Square Kilometre Array Pathfinder, pointed at a quiet, unremarkable patch of southern sky and found something that, by any reasonable understanding of how the universe is supposed to work, was not supposed to be there. A ring. A perfect, ghostly, almost geometric ring of radio emission, hanging in deep space, around 1,000,000 light-years across, with a single galaxy sitting at the dead center of it, like a coin dropped into a pond. They called it an odd radio circle. Internally, they just called it an ORC. And then they found another one, and another, and another, and another. A team led by Anna Kopinska and Ray Norris published the first ORCs in 2021. Within 2 years, ASCAP and South Africa's Meerkat Array had pushed the catalog to around half a dozen confirmed objects, and as new wide-area radio surveys come online, the number keeps quietly climbing. Now, here's the part that takes a moment to land. These rings are huge. A typical ORC, measured at the distance of its central galaxy, is between 250 and 500 kiloparsecs across. That is bigger than most galaxies. The Milky Way, our own galaxy, is around 30 kiloparsecs across. ORCs are the size of small galaxy groups, except they don't contain anything. They are just ring. Just radio emission, expanding outward, with one galaxy at the middle and a whole lot of nothing in between. For almost 4 years, the leading astronomers on the project, including Norris himself, who has spent his career looking at radio surveys, openly admitted on the record that they did not know what was making them. Then, in April of 2024, they finally caught one in X-rays. ORC-4, the best studied of the lot. And the X-rays, combined with optical and infrared follow-ups, pointed at a host galaxy whose stars are roughly 6 billion years old, with one short, intense burst of star formation that ended about 1 billion years ago. The current best guess is that the rings are shells of shocked gas blown out by enormous galactic winds during that ancient starburst, propagating outward at relativistic speeds for 1 billion years before they reach the size we see today. Which, if true, makes them something even stranger than a mystery. It makes them gravestones. Million light-year monuments to events inside a galaxy that ended back when the dinosaurs hadn't even started yet. We are looking at the cosmic echo of a burst of starlight that died on Earth before complex life existed, and the gravestone theory only covers ORC-4. The others are still on the table. Supermassive black hole mergers, galaxy collisions, shock bubble interactions, exotic things people don't put in press releases. The honest answer is, we are very early in figuring out what these things are, and the universe was apparently producing them quietly, in the dark, for billions of years before we built a radio telescope sensitive enough to notice. 1,000,000 light-year ring in empty space, with a galaxy at the center, that nobody, 4 years in, can fully explain. That's just the opening act. Number 11. 1,000 strands in the heart of the galaxy. Imagine looking at the center of our own galaxy, the supermassive black hole Sagittarius A star, the dense bulge of stars around it, the warm clouds of gas, and finding that the entire region is threaded with about 1,000 neat, pencil-thin vertical lines. Lines that are perfectly straight. Lines that are aligned with each other, almost like steel wool that has been combed by something invisible. Lines that nobody has been able to explain in 40 years. In the 1980s, an astronomer named Farhad Yousefzadeh at Northwestern University was looking at radio observations of the inner Milky Way and noticed that some of the brightest features were these long, thin magnetic strands, what astronomers call non-thermal radio filaments. He found around 24 of them. They glow because charged particles spiral along their magnetic field lines and emit synchrotron radiation, the way an electron in a particle accelerator emits light. 24 was already odd, They were 10 to 150 light years long, about 1 light year wide, all roughly perpendicular to the disk of the Milky Way, and nothing in any standard model of the galactic center cleanly produced anything like them. Then, in 2022, Yusuf Zadeh and his team published a series of papers using a new, wide-area mosaic from the Meerkat Array in South Africa. The count went from 24 to nearly 1,000. 1,000 vertical, magnetic threads stitched into the heart of our galaxy, organized in groups, with consistent orientations, spread across the inner few hundred light years of the Milky Way like the world's slowest tapestry. And here's where it gets quietly weird. Some of the leading theories tie them to past flaring episodes of Sagittarius A star, meaning the central black hole would have had to be vigorously belching cosmic rays into the surrounding magnetic field at some point in the recent geological past. Other theories point to a supernova remnant whose shockwave is interacting with the field. Other theories invoke an invisible, hot, stellar wind-driven bubble surrounding the galactic center. Nobody can prove any of them. Then, in 2025, a follow-up Meerkat survey reported finding another 164 mysterious compact radio rings near the galactic plane on top of the filaments. A whole second population of unexplained structures, sitting right next to the first. So this is where we are. The center of our own galaxy, the closest galactic nucleus we will ever have observational access to, is full of structures that look engineered, behave unpredictably, and have stood unexplained for 40 years and counting. We are not looking out at some distant exotic place. We are looking inward, at the gravitational core of the place we live, and the closer we look, the more strange threads we find. Number 10. A star older than the universe. In the constellation Libra, about 200 light years from Earth, there is a quiet, slightly orange subgiant called HD 140283. It has been sitting in the stellar catalogs since 1912. It does not pulse, it does not flare, it is not blowing up. It is just, in its own quiet way, the most embarrassing star in cosmology. In 2013, an astronomer named Howard Bond at Pennsylvania State University used the Hubble Space Telescope to get a new, very precise parallax measurement of HD 140283. Parallax is the gold standard technique for measuring stellar distances. You look at the star from one side of Earth's orbit, then from the other side 6 months later, and you measure how much it appears to shift against the background. Bond's team plugged the new distance into stellar evolution models and came out with a number: 14.46 billion years old. Take a second with that. The age of the universe, as measured by the cosmic microwave background, the leftover heat of the Big Bang, is 13.79 billion years, plus or minus about 20 million. So Bond's team had measured a single star that was, by their best estimate, around 650 million years older than the universe it lived in. The press immediately gave it a nickname, the Methuselah Star, after the biblical patriarch who supposedly lived for almost 1,000 years. Now, the proper science here is interesting, because over the next decade, follow-up work has slowly tightened the estimate. A reanalysis using better stellar models brought it down toward 14.1 billion. In 2025, a paper using astroseismology, the technique of measuring the tiny pulsations on the star's surface to infer its interior structure, landed on 14.2 billion years, plus or minus 400 million, within errors that overlaps the age of the universe. So mainstream cosmology can, and now does, say with a straight face that the Methuselah Star is not, technically, older than the universe. But here's the thing. Even the most generous current measurement, 14.2 billion years minus 400 million, means HD 140283 is at least 13.8 billion years old, which is, to within the precision we can possibly measure, the same age as the cosmos itself. For this star to exist in its current quiet form, it had to have formed from the very first generation of gas in the universe, within a few 100 million years of the Big Bang, before galaxies as we know them existed, before the cosmic dark ages had fully lifted, and it is still burning, 200 light-years from us, in our own galactic neighborhood. This is not a hypothesis. This is a star you can point a telescope at tonight if you're south of about 40 degrees latitude. A small, quiet, ancient witness to the youngest possible cosmos, sitting calmly in the night sky, just barely older than everything around it. The older than the universe framing is the version of the story that makes the news. The version that should make you uneasy is the version where the math just barely works out, where one stellar age measurement, sharpened by one telescope upgrade, would push HD 140283 back into paradox territory. We do not have a comfortable margin here. We have the universe insisting, by the thinnest possible thread, that this star is allowed to exist. If that thread ever breaks, the entire age of the cosmos gets reopened. Number 9. Explosions that do not fit any model. On the 16th of June, 2018, a telescope in Hawaii called ATLAS, the Asteroid Terrestrial Impact Last Alert System, registered a sudden bright flash in a small galaxy called CGCG 137-068, about 200 million light-years away. The flash was given the catalog identifier AT2018COW. The last 3 letters were just sequence assignment. They happened to spell cow. Astronomers being astronomers, the name stuck. The cow was odd. A normal supernova brightens over a week or two, peaks for a few days, and fades over months. The cow brightened in 2 days, peaked at an absolute magnitude near -20, about as bright as the entire galaxy it lived in, give or take, and then faded over weeks instead of months. Its spectrum, at peak, was a smooth, featureless, very blue glow. There were no clear absorption lines, no fingerprints of the heavy elements you'd expect from a stellar explosion. Just clean, hot, blue light, fading fast. A new class of cosmic explosion was born. Astronomers called it a fast blue optical transient, FBOT, or more formally, luminous fast blue optical transient, LFBOT. Then more of them showed up, sometimes by combing old surveys for missed events, sometimes in real time. CSS 161010, a T2020XND, a T2022TSD. The community started giving them barnyard nicknames. The camel, the koala, and then in 2023, there was the finch. A T2023FHN exploded in April 2023. The finch behaved like a cow, fast brightening, blue spectrum, weeks-long fading. But when astronomers chased down its host, they could not find a galaxy. They eventually located it. The finch had exploded in completely empty space between galaxies in the Vela cluster. Not in any host galaxy at all, but in the intergalactic medium, associated only with a single, faint, ancient globular cluster. Now, here's what that means in practical terms. The leading models for the cow involve a newly born millisecond magnetar, a young, hypermagnetized neutron star, buried inside a low-mass envelope of stellar material, spinning down and dumping energy outward. To make a young magnetar, you need a young, massive star. Massive stars live for a few million years before they die. They form in star-forming regions in galaxies. They do not form in empty intergalactic space, hundreds of millions of light-years from the nearest stellar nursery. But something exploded in that space, with all the characteristics of a young, violent stellar death, in a region of the cosmos that should be inert. Astronomers are still working on what the finch actually was. Some models invoke a tidal disruption event involving an intermediate mass black hole inside the globular cluster. Others involve the merger of two white dwarfs. Others quietly admit that nobody has a clean answer, and the underlying point is bigger than the finch. There is a population, small, rare, but real, of explosions in the universe that look like dying massive stars, but happen in places dying massive stars should not be, and behave on timescales. Dying massive stars should not behave. We do not have a clean, unified theory of what these things are, and we keep finding more of them. The sky is supposed to be a roughly understood neighborhood. Stars are born. Stars age. Stars die in well-categorized ways. We have models for each step. The cow and the camel and the koala and the finch are the universe, quietly noting that the categories are incomplete. Number 8. The lithium that should be there and isn't. Big Bang. Nucleosynthesis is one of the most successful predictions in the history of physics. It says that in the first 20 minutes after the Big Bang, when the universe was hot enough and dense enough for nuclear fusion to happen everywhere at once, the protons and neutrons in the primordial soup combined to make the first atomic nuclei. Hydrogen, helium, a trace amount of lithium, a whisper of beryllium. And the theory does not just say roughly how much of each. It says with precision that after the universe cooled and the reaction stopped, the cosmic abundance of deuterium, heavy hydrogen, should be about 2.5 parts in 100,000. The abundance of helium-4 should be 24% by mass. The abundance of helium-3 should be about 1 part in 100,000. The abundance of lithium-7 should be about 5 parts in 10 billion. We have measured all of these. Deuterium matches. Helium-4 matches. Helium-3 matches. Lithium-7 is off by a factor of 3 to 4. This is the cosmological lithium problem, and it has stood since Francois and Monique Spite published their measurements of ancient halo stars in 1982. Here is what the Spites did. They reasoned that the oldest, most metal-poor stars in our galaxy, stars formed from gas that had barely been polluted by previous generations of stellar nucleosynthesis, should still carry in their atmospheres the original lithium abundance that the Big Bang produced. They looked at hundreds of these stars. They got a number. The number was 1.6 parts in 10 billion. Big Bang nucleosynthesis predicts roughly 5 parts in 10 billion. 3 to 4 times too little lithium in the universe. Now, here's the thing. For 40 years, people have been trying to explain this away. Maybe the stars destroy lithium as they age, sinking it down into their interiors where it gets burned. Maybe the nuclear cross-sections we use in the calculation are slightly wrong. Maybe the cosmic baryon density is slightly off. Maybe there is some exotic decaying particle from the dark sector that interferes with primordial reactions. Each of these solutions can patch the lithium-7 problem on its own. But each of them also tends to break one of the other Big Bang nucleosynthesis predictions that does match: the deuterium, the helium-4, the helium-3. You cannot scrape lithium-7 down to the observed level without also putting your finger on a scale that is currently very accurately balanced. And then there is the truly weird thing. The Spite plateau, the lithium measurement across all those ancient stars, is flat. It is the same value, within tiny scatter, in stars all over the galactic halo. If stars were quietly destroying lithium in their interiors, you'd expect different stars to have destroyed different amounts, and you'd see scatter in the measurement. Instead, you see a beautifully flat plateau, which means either every metal-poor star in the galaxy is destroying lithium at exactly the same rate, in exactly the same way, with no scatter, or the actual primordial value of lithium-7, the value the universe was actually born with, is different from what the theory predicts. In the last decade, more sophisticated stellar diffusion models, atomic diffusion, plus a parameter called turbulent mixing, have done a much better job of explaining the plateau through stellar destruction. Most contemporary nuclear cosmologists now treat the lithium problem as a stellar physics issue rather than a true cosmological one. But treat as is not the same as have proven. 40 years on, every cosmology textbook still gets to brag that Big Bang nucleosynthesis is one of the best confirmed theories in physics. And quietly, in the same chapter, 3 to 4 lithium nuclei out of every 5 that the theory says should exist are quietly missing. The universe is keeping count, and the count does not add up. Number 7. Antimatter that should not be here. In May of 2011, the Space Shuttle Endeavour carried up to the International Space Station a refrigerator-sized $2 billion scientific instrument called the Alpha Magnetic Spectrometer, AMS-02. It was designed by a team led by Nobel laureate Samuel Ting at MIT. Its job was simple and ambitious. It was going to be the most sensitive antimatter detector ever flown above Earth's atmosphere. For 15 years, AMS-02 has been quietly sitting on the outside of the space station, sifting through cosmic rays. Hundreds of billions of charged particles have streamed through its detector. It has produced extraordinary measurements of positrons, antiprotons, and high-energy cosmic ray spectra. And somewhere in that pile of data, it has detected, apparently, about 8 candidate anti-helium nuclei. Now you need to understand what that means. In a universe that is overwhelmingly made of matter, anti-helium does not happen. Positrons happen. Antiprotons happen. They get produced in tiny quantities when high-energy cosmic rays collide with the gas between stars. But the cross-section for spontaneously producing an entire anti-helium nucleus, 3 or 4 antiquark-bound nucleons in a single particle, in the same kind of collision is suppressed by factors of around 10 to the minus 13th. So if AMS-02 sees 8 anti-helium candidates among billions of helium nuclei, that is roughly a factor of 1,000 times more anti-helium than secondary processes can naturally produce. If those candidates are real, they are not background, they are signal, and the signal does not have a comfortable interpretation. The leading possibilities are uncomfortable on purpose. Either there are pockets of the universe, entire distant galaxies even, made of antimatter, which is supposed to have been almost entirely annihilated in the first second after the Big Bang. Or dark matter, whatever it is annihilating somewhere in the galactic halo and producing anti-helium as a byproduct, which would require very specific particle physics that is not in the standard model. Either answer rewrites a chapter of cosmology. And here's the thing. Samuel Ting first publicly disclosed the candidates at a conference at CERN in December of 2016. We are now nearly a decade later. The official, peer-reviewed AMS-02 analysis of the anti-helium events has still not been published. That is not because the collaboration is uninterested. It is the opposite. They have spent 10 years trying to rule out every possible source of contamination. Every way the detector could possibly misidentify a normal helium nucleus as an anti-helium nucleus. Every isotope confusion. Every weird backscattering event. Because they know that if they get this wrong, they will have to walk it back in front of every physicist on Earth. In the meantime, a separate experiment called GAPS, the General Antiparticle Spectrometer, is being flown by balloon over Antarctica, specifically designed to look for cosmic ray anti-helium and anti-deuterium and confirm or refute the AMS signal. If GAPS finds it, the conversation changes overnight. If GAPS does not find it, the AMS candidates quietly go away as instrumental artifacts. But sitting on the International Space Station right now, in a detector that has been running for almost a decade and a half, are 8 pieces of antimatter that, if real, are not allowed by our model of how the universe is. And the people who built it are still not sure whether to tell us. Number 6. A void that pushes us. For decades, astronomers have known that the Milky Way is not sitting still. It is moving at 630 kilometers per second with respect to the cosmic microwave background, the leftover heat of the Big Bang, which provides a kind of natural cosmic rest frame. For a long time, the assumption was that we knew why. About 600 million light-years away, there is a massive concentration of galaxies called the Shapley concentration. The Shapley concentration is the densest, most massive structure in the nearby universe, and its gravity is pulling the entire local group, our galaxy, Andromeda, the dozens of dwarf galaxies that come with us, slowly toward it. The pull explains the motion. End of story. Or so it seemed. In January of 2017, a team led by Yehuda Hoffman at the Hebrew University of Jerusalem, working with Daniel Pomerade, Brent Tully, and Hélène Courtois, published a paper in Nature Astronomy called The Dipole Repeller. What they did was build a three-dimensional reconstruction of the motion of every galaxy in our cosmic neighborhood, using a dataset called Cosmic Flows 2. They modeled all the gravitational pulls and pushes simultaneously. And they discovered that the Shapley concentration, by itself, is not actually strong enough to account for the Milky Way's 630 kilometer per second motion. Shapley supplies about half of it. The other half comes from a region of the universe in the opposite direction, a region with almost nothing in it. They called it the dipole repeller. The dipole repeller is, to a first approximation, a very large underdensity, a vast pocket of cosmic emptiness, roughly 500 to 700 million light-years from us. It does not contain meaningful clusters or galaxies. It contains far less matter than the average region of space. And here's the thing. The dipole repeller is not literally pushing us anywhere. There is no anti-gravity. There is no negative mass. What is actually happening is more subtle and more philosophically uncomfortable. Everywhere else in the universe is pulling on us. The Shapley concentration is pulling hard on one side. Other clumps of mass are pulling more gently from other directions. The dipole repeller, being almost empty, is pulling much less than the average region in that direction. So, we appear to be pushed away from it. Emptiness has gravity, not because it contains anything, but because everything else does. The two effects, the Shapley pull and the apparent dipole repeller push, turn out to be almost exactly equal. They contribute roughly half each to the velocity of the Milky Way through the cosmos. Half of our motion through the universe is being driven by something that is not there. You will not see the dipole repeller in any photograph. There is nothing to take a photograph of. You will not point a telescope at it and see a void in the way you'd see a building. It is defined entirely by its gravitational signature on everything around it, by the careful reconstruction of how every other galaxy in the local universe is moving, with us at the center of the calculation. In a real sense, you cannot point at the dipole repeller. You can only point at the place we are running away from, and we have been running away from it for the entire history of our galaxy. Number 5. Something invisible punched through our galaxy. If you orbit the Milky Way and you look carefully, you start to notice scars. Long, thin streams of stars stretching across the sky, all moving together, all roughly the same age, all roughly the same chemistry. These are stellar streams. The slow motion remains of small galaxies and globular clusters that wandered too close to the Milky Way and got torn apart by its gravity. The Milky Way is, in a real sense, a slow eater, and the streams are the crumbs. The longest, thinnest, most prominent stellar stream in the galactic halo is called GD-1. It stretches more than 100 degrees across the sky and reaches about 10 kiloparsecs in length, roughly the diameter of the entire disk of the Milky Way. It is the chewed-up remains of an ancient, low-mass globular cluster that was destroyed by the Milky Way's tidal field long ago. Now, in 2018, two astronomers, Adrian Price Whelan at the Flatiron Institute and Anna Banaka, then at Harvard, did something very careful. They combined the Gaia satellite's precision measurements of stellar proper motions with photometry from the Pan-STARRS survey. Together, those two datasets let them filter out the background stars of the Milky Way and isolate almost cleanly the stars that actually belong to the GD-1 stream. When they did that, they could see the stream's shape with unprecedented clarity for the first time. And in the shape, there was a gap, a clean, sharp, distinct gap in the stream, with a sideways spur of stars displaced from the main track, as if something had reached in and pulled them off. The shape of the gap and spur is, mathematically, very specific. It looks exactly like what you'd get if a dense, massive object, anywhere from 1 million to 100 million solar masses, had passed through the stream relatively recently and gravitationally kicked the stars near its trajectory sideways. The morphology is so distinct that you can essentially reverse engineer the perturber's mass, speed, and approach angle from the wreckage. Banaka and Price Whelan did exactly that. Then they went looking for the object. The mass range, 1 million to 100 million solar masses, overlaps the masses of dwarf galaxies and globular clusters. So the obvious first move was to check whether any known luminous object in the Milky Way's halo could have crossed the GD-1 stream's path at the right time, with the right trajectory. None of them could. Every known dwarf galaxy, every globular cluster, every giant molecular cloud, each one was eliminated by orbit matching or density arguments. The dwarf galaxies were too far away or moving in the wrong direction. The globular clusters were too dispersed to make a sharp gap. Molecular clouds at the relevant distances were too diffuse to do the kicking. There is, as far as anyone has been able to find, no luminous candidate for the thing that punched through the GD-1 stream, which leaves a dark candidate. The leading hypothesis since the original Banaka paper is that the perturber was a dark matter subhalo, a clump of pure invisible dark matter with a mass somewhere between a small dwarf galaxy and a large globular cluster, threading through the galactic halo. Standard models of cold, dark matter actually predict that the Milky Way should be surrounded by thousands of these things, with no stars in them, completely invisible except by their gravity. GD-1 may be the first direct fingerprint of one. In 2024, a follow-up paper went a step further. It suggested that the specific morphology of the gap and spur was best explained not just by a dark matter subhalo, but by a core-collapsed self-interacting dark matter subhalo. Self-interacting meaning that the dark matter particles in the clump are not just bumping inertly around. They are interacting with each other through some hidden force, in a way that the standard lambda cold dark matter model does not include. If that is right, the gap in GD-1 is not just evidence that dark matter exists. It is evidence that dark matter has its own physics, its own forces, its own internal dynamics, a whole hidden sector with its own rules. The community has been notably careful about how to talk about this. The paper was not heavily promoted. The press did not, by and large, frame it as, "We have found dark matter." But the wreckage is sitting there in the Milky Way's halo, photographed in fine detail, and the only candidate that fits the calculations is something that does not emit light. The galaxy carries the footprints of things we cannot see. Number 4. A galaxy without stars. About 300 million light-years from Earth, in the constellation Coma Berenices, there is a swarm of more than 1,000 galaxies called the Coma Cluster. It is one of the closest large galaxy clusters to us, and one of the most studied. Astronomers have been looking at it carefully for nearly a century. In 2016, a team led by Peter Van Dokkum at Yale University discovered something in it that had been sitting there in plain sight the whole time. they were using an unusual telescope. It is called the Dragonfly Telephoto Array, and instead of being one big traditional mirror, it is 48 commercial telephoto camera lenses ganged together into a single panoramic instrument. The advantage is that it is exquisitely sensitive to extended, low-surface brightness objects, things that are big but barely glowing, ghostly things. Dragonfly found 47 new galaxies in the Coma cluster that had been missed by every previous survey. Each one was huge, faint, and diffuse, what astronomers call ultra-diffuse galaxies. The largest of them was given the catalog name Dragonfly 44. Dragonfly 44 is the size of the Milky Way. Dragonfly 44 emits about 1% of the Milky Way's light. That is the first thing that does not add up. A galaxy as big as ours should have, roughly, as many stars as ours. But the photographs showed only a sparse smear of dim, faint stars across an enormous extended halo. It looked like an ordinary spiral galaxy that had been almost entirely erased, leaving only an outline. Van Dockum's team spent 6 nights on the Keck Observatory in Hawaii, measuring the velocities of the stars they could see. The faster stars move in a galaxy, the more total mass is gravitationally holding them in. The math is straightforward. You measure the velocity dispersion, you derive the total mass. Dragonfly 44's velocity dispersion was huge. The stars were whipping around as if the galaxy contained, in total, around 1 trillion solar masses of material. Milky Way scale. The visible stars, summed up, came to about 100 million solar masses. The other 99.99% of the galaxy is dark. Dragonfly 44 is roughly 99.99% dark matter. Almost all of its mass is invisible. The few stars it does have are essentially decoration, a faint trace pattern through an enormous gravitational ghost. And here's the thing. The galaxy is also surrounded by roughly 100 globular clusters, small, dense bundles of ancient stars that orbit galaxies like satellites. The number of globular clusters around a galaxy scales fairly cleanly with the galaxy's total mass. The Milky Way has around 150. Dragonfly 44 has around 100. By every gravitational tracer, stellar velocities, globular cluster count, Dragonfly 44 is a Milky Way class galaxy. By every photometric tracer, it is barely there. The follow-up work has not made this go away. A retrospective in Quantum magazine in 2022, 6 years after the discovery, used the word mystery without qualification and quoted the lead authors as saying the Dragonfly 44 problem had only deepened. There are now hundreds of confirmed ultra-diffuse galaxies in the Coma cluster and other clusters. Some of them appear, ironically, to have very little dark matter, which is even harder to explain. Some, like Dragonfly 44, appear to be almost pure dark matter wrapped in a thin veil of stars. If the cosmic web is full of galaxies like this, and the growing surveys suggest it might be, then everything we thought we knew about the total amount of matter in the universe is off. We have been counting galaxies by their light. We have been doing a census of the cosmos by photographing the bright parts. The dark parts have been keeping their own counsel. Number 3. Invisible black holes from the first second. In 1966, 2 Soviet physicists, Yakov Zeldovich and Igor Novikov, asked a quiet question. The early universe, in the first second after the Big Bang, was unimaginably hot and dense. In some regions, the density would have been slightly higher than average, just by random quantum fluctuation. If a region were dense enough, denser than the threshold for gravitational collapse, could it collapse directly into a black hole without ever needing a star? Their answer was yes, in principle, and the black holes that resulted would be unlike anything else in the cosmos. In 1971, Stephen Hawking picked the question up and ran with it for an entire paper. He worked out the population statistics, the mass spectrum, the lifetimes. He called them primordial black holes, and he never stopped thinking about them. Here is what makes primordial black holes different. A stellar black hole, the kind we usually talk about, forms from the collapse of a massive star. It has a minimum mass, roughly 3 solar masses, set by the physics of stellar death. Below that, you get a neutron star instead. A primordial black hole has no such lower limit. If a region of the very early universe was the right shape and density, it could have collapsed at any mass, from far below an asteroid all the way up to many solar masses, or more. There are theoretical scenarios in which primordial black holes weigh as much as a small mountain, or as much as a planet, or as much as a galaxy. And crucially, they emit essentially no light. They are not embedded in accretion disks. They are not bound to companion stars. They are not visible to any telescope we have. They could be coasting through interstellar space in vast numbers, completely undetected, if the asteroid mass window, roughly 10 to the 17th to 10 to the 22nd grams, is populated by primordial black holes. Those black holes could account for 100% of the dark matter in the universe. That is the prize. That is the thing that would make this an item 1 on a different video. Now, here's where it gets interesting. In 1998, Hawking died, not knowing whether his black holes existed. But in 2015, when LIGO began detecting the first gravitational waves, the very first event, GW 150914, was surprisingly massive. 2 black holes, 29 and 36 solar masses, merging 6 billion light-years away. That was heavier than astronomers expected stellar mass black holes to commonly be. Several papers immediately suggested that some fraction of LIGO's detections might actually be primordial black holes. The community largely walked that back. Standard astrophysics could just about explain it. Then, in November of 2025, the LIGO, Virgo, and CAGRA collaborations released a brief, careful statement about a candidate event called S251112CM. The signal indicated a merger involving at least one object that was lighter than the Sun, a sub-solar mass black hole. That is the smoking gun. Subsolar mass means you cannot make it from a star. Stellar collapse cannot produce a black hole below the 3 solar mass floor. If S251112CM is real, and that is still a careful if, because it is right at the edge of LIGO's sensitivity, it is direct gravitational wave evidence of a primordial black hole, a black hole born in the first second of the universe. The implication is enormous. If even a small population of primordial black holes exists at any mass, then a portion of dark matter is, at last, something we can detect. And if the asteroid mass window is populated, the universe contains an unfathomable number of these objects. Tiny, coasting, invisible, threading through galaxies and dark matter halos. Researchers at JPL and Harvard are now actively combing seismic data and lunar laser ranging archives for the faint signatures that a small primordial black hole would leave if it passed through the Earth. At the asteroid mass scale, the calculation suggests one of them could pass through our planet roughly once every 10,000 years. Sit with that for a second. The Earth, on geological timescales, may be quietly being threaded by dark matter in the form of small black holes, on the order of once every 10 millennia. We would not see them. We would not feel them. They would deposit almost no energy as they passed. They would leave a faint pressure wave, maybe a faint seismic ring, in instruments we did not yet have the sensitivity to interpret. Stephen Hawking spent the last years of his life arguing for primordial black holes, and never lived to see one. If the November 2025 LIGO candidate is what it looks like, he was right. And dark matter, the largest unsolved mystery in physics, may turn out to be a population of invisible black holes that have been reigning quietly through the Earth on a timescale longer than any civilization will ever last. Number 2. A signal from the first stars that was twice too loud. About 180 million years after the Big Bang, the universe was almost completely dark. Hydrogen filled space. The first stars had not yet ignited. The cosmic microwave background, the leftover heat of creation, had cooled into a faint radio glow. Then, somewhere, the first star switched on. Then another. Then another. Their ultraviolet light spread outward, scattered through the neutral hydrogen, and changed the way that hydrogen interacted with the cosmic microwave background. Specifically, the radiation at 21 centimeters, the famous 21 centimeter line, the natural radio fingerprint of neutral hydrogen, got absorbed slightly more than it otherwise would have. If you could measure the precise depth of that absorption from Earth today, you would be measuring, almost directly, the moment that the first stars in the cosmos turned on. You would be measuring the cosmic dawn. This is what an experiment called EDGES. The experiment to detect the global epoch of Ryanization signature was built to do. EDGES was led by Judd Bowman of Arizona State University. It is not a glamorous instrument. It is a flat, low-profile radio antenna sitting in the remote Western Australian desert, hundreds of miles from the nearest city, surrounded by radio-quiet land. In March of 2018, EDGES published in Nature. The signal was there. The absorption dip at the predicted frequency of 78 megahertz was real. The team had found it. The cosmic dawn was detected for the first time with a single antenna in the desert. The story should have ended there. It was the most important measurement in radio cosmology in a decade. There were press releases, news segments, scientific committees fast-tracking funding for follow-up. But there was a problem. The EDGES dip was twice as deep as standard cosmology allows. The maximum depth of the cosmic dawn absorption signal, according to all the physics we currently understand, is around 0.2 Kelvin. EDGES measured about 0.5 Kelvin. That difference does not go away with better calibration. It is huge. It means either the hydrogen gas in the early universe was much colder than physics predicts, or the radio background was much hotter, or some combination of the two. Within months, theoretical physicists were writing papers. The leading explanation, by Renan Barkana at Tel Aviv University, was that the gas had been cooled by an undiscovered sub-GeV millicharged dark matter particle, a kind of dark matter that interacts very weakly with ordinary matter through a tiny electric charge. Such a particle would cool the cosmic gas through gentle, persistent thermal contact. If EDGES was right, we had glimpsed dark matter touching normal matter, faintly, billions of years ago, at the very edge of the first stars. Other explanations were proposed: early radio sources, exotic cosmic string interactions. None of them were tidy. The community knew exactly what it needed. An independent experiment, built with different hardware, in a different location, looking at the same frequencies, would either confirm EDGES or not. The experiment was called CERES-3. It was led by Saurabh Singh and operated in southern India. It was specifically designed to either reproduce or refute the EDGES signal. In 2022, CERES-3 published its result. They could not find the signal. In fact, CERES-3 reported that they could rule out the EDGES best fit profile at 95.3% confidence. So now, we are stuck. Either EDGES was wrong, confused by some subtle systematic effect, some scrap of foreground galactic emission misinterpreted as a cosmic signal, and the first stars have not actually been observationally confirmed yet. Or EDGES was right, and CERES-3 missed it because of some other subtlety nobody yet understands. Either way, the answer is that we cannot currently measure the moment the first starlight in the universe turned on. We had a candidate detection. We had a follow-up that disagreed. And the cosmological community has, more or less, quietly moved on, waiting for the next generation of experiments, the reach array, the SKA low, to settle the matter sometime later this decade. That is the calm, scientific version of what is happening. Here is the version that should keep you up at night. A single antenna in a desert in 2018 may have either accidentally hallucinated the cosmic dawn or actually captured it and seen, in the depth of the signal, that there is a particle in the early universe doing things our model of physics does not allow. We do not know which, and in the meantime, the literal first light in the cosmos remains an open question. The way the universe began was almost certainly recorded in that 21 centimeter signal. The recording is still on a hard drive in Tempe, Arizona, and a desert in southern India, and the question of what is actually on it has not been answered. Number 1. The first things that ever shone were not made of normal matter. In 2007, 3 physicists, Catherine Fries at the University of Texas at Austin, Doug Spolier, and Paolo Gondolo, published a paper that asked an honest, simple question. In the very early universe, when the first clouds of pristine hydrogen and helium were collapsing under their own gravity to form the first stars, those clouds would have been forming inside concentrated halos of dark matter. The dark matter, whatever it is, would have been present in much higher concentration in the early universe than it is now. If dark matter is the right kind of particle, a weakly interacting massive particle, a WIMP, it would have been self-annihilating, slowly, inside those collapsing hydrogen clouds. What would happen, the 3 of them asked, if the energy released by dark matter annihilation inside a primordial gas cloud was more than the energy radiated away by the gas as it collapsed? The answer was that the gas would stop collapsing. It would stabilize. It would form a giant, diffuse, smoky hydrogen and helium ball, swelling outward against its own gravity, kept hot not by nuclear fusion, but by the slow, steady annihilation of dark matter trapped in its core. This object would be a star, but it would not be powered by fusion. It would be powered by dark matter. Its surface would be much cooler than a normal star's, around 10,000 Kelvin instead of the millions inside a fusion-powered core. Its color would be a deep, cool blue. Its mass could grow, in principle, to 1 million solar masses or more, far heavier than any star fusion can sustain. Its luminosity could reach 1 billion times that of the sun. Fries named them dark stars. For 16 years, dark stars existed only on paper. There was no telescope sensitive enough to look for them at the redshifts where they should have lived, the first 300 to 400 million years after the Big Bang. The James Webb Space Telescope changed that. Webb launched in December of 2021. By 2023, it was returning images of objects at higher redshift than any telescope before it had ever seen. Among those objects, in a deep survey called JADES, were 3 sources at extreme distances: JADES-GS-Z11-0, JADES-GS-Z12-0, and JADES-GS-Z13-0. Each one was, when first measured, brighter and more compact than any normal galaxy at that redshift was expected to be. In July of 2023, Cosmin Ely at Colgate University, with Gillian Paulin and Catherine Fries, yes, the same Catherine Fries who had proposed dark stars 16 years earlier, published a paper in PNAS. They had taken the 3 JADES sources and compared their photometric spectra to the predicted spectra of supermassive dark stars. All 3 were consistent. That is, the light coming from each of those 3 objects at the very edge of the observable universe could be explained either by a strange, unusually compact early galaxy, or by a single, enormous dark star powered by dark matter annihilation. In 2025, a follow-up using JWST's NIR spec instrument, the spectrograph, which gives much more detailed spectral information than the photometry alone, confirmed that 2 of the 3, JADES-GS-Z11-0 and JADES-GS-Z 13-0 remained spectroscopically consistent with the dark star interpretation. Two additional candidates were added, JADES-GS-Z14-0, the most distant luminous object ever observed by humanity, and JADES-GS-Z14-1. Now, none of this is technically proof. It is possible that all of these objects are just very compact, very luminous, very early galaxies. Galaxies that were able to form much earlier than our standard model of cosmology predicts, perhaps with the help of unusually heavy black hole seeds. The mainstream interpretation, by and large, prefers this explanation. But here is the thing. JWST has been finding, over and over again, that the early universe was full of objects that are too bright, too massive, and too well formed for the first few hundred million years after the Big Bang. This is sometimes called the impossibly early galaxies problem. Standard cosmology has been quietly straining to accommodate them. If the dark star interpretation is right, that problem goes away. The early universe was not full of impossibly early galaxies. It was full of dark stars, single objects, masquerading in the photometry as galaxies, lit by the slow annihilation of dark matter in their cores. If that is true, then the very first thing in the universe that emitted light, the literal first light, the source that lifted the cosmos out of darkness, was not a normal star. It was an object made of normal hydrogen and helium, but lit from within by something we still cannot directly detect in any laboratory on Earth. Stop and feel that for a second. The first thing to ever shine in the universe was, possibly, the first object in the history of everything that was not made of normal matter alone. Dark matter, the substance that makes up most of the mass of every galaxy, the substance that we have been trying for 50 years to capture in xenon-filled vats and underground caverns, the substance that has refused, so far, to allow us to see it directly. That substance, in the dark star picture, would have been the original fuel that lit the cosmos. The mainstream is hedging. The community is calling these things candidates. The community is not yet announcing them. And the reason the mainstream is hedging is not skepticism. It is the opposite. They know that if dark stars are real, the textbook on cosmic history changes overnight. The first chapter, the chapter on how the cosmos first started to shine, has been wrong since it was written. We are looking out at light from the edge of the observable universe. We are looking at sources from the first few hundred million years after everything began. And we may be looking at the cosmic dawn. We may be looking at 3 pinpricks of light in the deepest images Webb has ever taken that are the universe quietly admitting that its very first witnesses were not normal stars at all. They were the first time anything in existence shone with the fuel of the dark. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.